Hello and welcome to another Algebra 2 video by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 4, Lesson 5 on the method of common bases. This is a new algebraic technique that you haven't seen before, so let's jump right into it. Alright, simple exponential equations. There are really very few algebraic techniques that do not involve technology to solve equations that contain exponential expressions. And by that I mean where the variable is in the exponent. In this lesson, we will look at one known as the method of common bases. Let's start right away with an easy-ish problem in exercise number 1. Solve each of the following simple exponential equations by writing each side of the equation using a common base. So just keep in mind, right, whenever we have something that looks like, I don't know, 5 to the 7th, all right, just so that we all have the same terminology, this is the base, and this is the exponent. So when we say write each side with a common base, we want the number that's sitting down here to be the same in each case. All right, so, right, I've got 2 to the x equals 16. Now what that is essentially saying is find the power that I have to raise 2 to in order to get 16. It is very important in this lesson to generally kind of be able to think about small powers like 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th is 32, and likewise with 3, 4, 5, 6, maybe even 7, okay? So this one's pretty easy, right? If 2 to the x is 16, what we can do is rewrite this as 2 to the x equals 2 to the 4th, right? Because 16 is the same as 2 to the 4th. Don't be confusing that with 4 to the 2, or 4 squared, which is also 16. But now we can literally say, x must equal 4. Right? Simple enough. Likewise, 3 to the x equals 27. Well, right, 3 squared is 9. 3 cubed is 27, 3 to the 4th is 81, etc. So I can say 3 to the x is equal to 3 to the 3rd, in which case I can now say x is equal to 3. Now, letter C is more challenging because I have 5 to the x is equal to 1 over 25. Now, one thing I should know for certain is that 25 is 5 squared. So I can certainly say 5 to the x is equal to 1 over 5 squared. Last thing I would want to then conclude, though, is that x is equal to 1/2, because it certainly isn't, right? In fact, now I should say, well, 5 to the x is equal to 5 to the negative 2, right? Because 1 over 5 squared is the same as 5 to the minus 2. And therefore x is equal to negative 2. All right, and now the most challenging one, right, at least for right now. In letter D, we have 16 to the x is equal to 4. Now that's a little bit tricky because I'd really love to write that 4 as 16 raised to some power, right? And if you think about it, 16 to the 1st is 1, 16 to the 2nd, that's even harder, is 256. 16 to the 0 is equal to 1, 16 to the negative 1 is equal to 1/16, 16 to the minus 2 is equal to 1 over 256. So how do 16 and 4 relate? Well, recall, obviously, that the square root of 16 is equal to 4. But that means that 16 to the 1/2 is equal to 4. So I can now say 16 to the x is equal to 16 to the 1/2, in which case x equals 1/2. Okay, now this is just this idea. If we can take the two sides of an exponential equation and write each side with the same base, then we can set the exponents equal to each other. Let's take a look at things that are a little bit more complicated. Now, before we get into more complex equations, what we want to do is look at an important exponent property. In each of the previous cases in exercise number 1, we could manipulate the right-hand side of the equation so that it shared a common base with the left-hand side of the equation. We can exploit this fact by manipulating both sides so that they have a common base. First, though, we must review an exponent law. Probably the most important exponent law that we work with in this particular unit. Let's take a look at exercise number 2. Simplify each of the following exponential expressions. All right. Now, in each one of these cases, we have a quantity raised to an exponent raised to another exponent. And that's where the product property of exponents come in. Whenever we have something raised to an exponent raised to another exponent, we multiply those two exponents. Let's take a look at letter A together. Here we have, and let me write it a little bit bigger for you, 2 to the third raised to the x. We can, quote, simplify this by simply rewriting it as 2, maybe make sure that looks a little bit more like a 3, 2 to the 3x. And each one of these is simply exactly like what we just did. So pause the video now and rewrite each one of these particular expressions using the product property of exponents. All right, in letter B, we have 3 squared raised to the 4x. So that's just going to then be 3 to the 2 times 4x. And that's going to be 3 to the 8x. Let's just go through each one of them. In letter C, we have 5 to the minus 1 raised to the 3x minus 7. That's going to then be 5 to the negative 1 times 3x minus 7. And that's going to be 5 to the negative 3x plus 7. And finally, 4 to the negative third raised to the 1 minus x squared is going to be 4 to the negative 3 times 1 minus x squared. And that's going to be 4 to the negative third plus 3x squared. Now, it would be very understandable if you're saying to yourself right now, I don't see how that has anything to do with the first problem. That would be very, very understandable. So let's now take the first problem, along with this one, put it together to see the method of common basis. Exercise number 3. Solve each of the following equations by finding a common base for each side. First equation, 8 to the x equals 32. And let me write this again a little bit bigger just so that we have a better ability to discuss it. Now, if this was a problem similar to exercise number 1, and it looks like one, what we would be looking for is some kind of power we could raise 8 to in order to get 32. The problem is 8 to the first is 8, 8 to the second is 64, and we've kind of just skipped right over anything that might give us 32. So now what we want to do is we want to think about the numbers 8 and 32 and whether or not each one of those could be written as a common base. Well, one thing we definitely should know is that 2 to the third is 8. So, just over here, right? 2 to the second is 4, 2 to the third is 8, 2 to the fourth is 16, 2 to the fifth is 32. And look at that, right? Both the number 8 and the number 32 can be written as 2 raised to some power. So what I'm now going to do is I'm going to replace this with 2 to the third to the x is equal to 2 to the fifth. All right, I'm just replacing 8 with 2 to the third, 32 with 2 to the fifth. I can now use the product property of exponents to rewrite the left-hand side of this equation as 2 to the 3x. The right-hand side I'm going to just leave as 2 to the fifth. And now, since they have a common base, right, a 2 here and a 2 here, I can now set their exponents equal to each other. I'm not canceling the 2's, by the way. I am just recognizing the fact that if I have 2 to the 3x equal to 2 to the fifth, then 3x must be 5. That allows me to now divide by 3 on both sides, and x is equal to 5/3. All right. When you use the method of common bases, and it only is applicable in certain times, right, when we can write both of them with the same base, we always want to think about small number bases. 2, 3, 4, Although oftentimes if you're thinking 4, 2 would have done the job anyway because 4 is a power of 2. So maybe 2, 3, 5, 6, 7, 8 again is the power of 2, so that's more questionable, right? 9 is a power of 3, etc. Let's take a look at letter B. 9 to the 2x minus 1, or sorry, 9 to the 2x plus 1 is equal to 27. Now, both 9 and 27 are somehow related to the number 3. So I want to see if you can try to pull this off. Maybe if you need to, write down powers of 3 here and see if you can solve that equation. All right, well, let's write down those powers of 3 really quickly. Get rid of all that. All right, we know that 3 squared is 9. 3 cubed is 27. I don't even have to go any farther than that, right? Because I have a 9 and a 27, and both of those can be written with powers of 3. So what I'm going to do is I'm going to take 9 to the 2x plus 1, and I'm going to rewrite it as 3 squared to the 2x plus 1. Notice how I'm trying to be good about my parentheses. Is equal to 3 cubed. I'm now going to use the product property, and I'm going to multiply that 2 through the 2x plus 1, so I'll get 3 to the 4x plus 2 is equal to 3 cubed. Now that I've got that common base of 3, I'm not going to divide it out, I'm just going to state the obvious. 4x plus 2 must be equal to 3. That means 4x must be 1, and x must be 1/4. And there it is, right? But the key is I must find those common bases. So what I'd like you to do now is pause the video and see if you can figure out what the solution to letter C is. All right, well, when I see something like 125 and 1/25, I'm thinking about 5, right? So 5 squared is 25. Right? 5 cubed is 125. And that should really be enough for me because I can then take 125 and write it as 5 to the 3rd raised to the x. And on this side, I can write 1/25 as 5 to the minus 2 to the 4 minus x. Now I can use that product property. I'll have 5 to the 3x is equal to 5 to the negative 8 plus 2x. All right, just multiplying through by that negative 2. Now I can set 3x equal to negative 8 plus 2x, subtract an 2x from both sides, and we find that x must be equal to negative 8. All right, that's the method of common bases. Let's see if you can do a multiple choice problem. Exercise number 4. Which of the following represents the solution set to the equation 2 raised to the x squared minus 3 is equal to 64? All right, well, play around with this one a little bit and see what you can find. All right, let me make this equation a little bit bigger so that you can see it on your screens. That's 2 to the x squared minus 3 is equal to 64. Now, we can't really do much with that 2. That's as small as it's going to get, right? So we really have to be looking at that 64 and thinking about possibly if it's a power of 2, right? We already know 2 to the 3rd is equal to 8. 2 to the 4th is equal to 16. 2 to the 5th is equal to 32. 2 to the 6th is equal to 64. And there it is. Right? 2 to the 6th is equal to 64. So I'm going to rewrite this as 2 to the x squared minus 3 is equal to 2 to the 6th. I can now say that x squared minus 3 is equal to 6, which tells me that x squared is equal to 9, which tells me x must be plus or minus the square root of 9, and that means x must be plus or minus 3. Choice 1. All right, and that's it, right? So the method of common bases is kind of cool, but it's only going to work if you can take these two exponential expressions on both sides of the equation and write each of them as the same number raised to some power, okay? Of course, the two powers will be different, but you've got to at least have the same base. Now, this technique can be used in any situation where all the bases involved can be written with a common base. In a very practical sense, this is rather rare, all right? It just is. Yet, these types of algebraic manipulations help us see the structure in exponential expressions. They also allow us to practice things like common powers of small integers or small whole numbers, as well as thinking about things like positive and negative powers. So let's take a look at exercise number 5. Two exponential curves, y equals 4 to the x plus 5 halves, and y equals 1/2 raised to the 2x plus 1, are shown below. They intersect at point A. A shaded rectangle has one vertex at the origin and the other at A as shown. We want to find its area. Letter A. Fundamentally, what do we need to know about a rectangle to find its area? All right, this should be pretty easy. Why don't you pause the video and go ahead and answer letter A. Well, you could say its width and its height, or its base and its length, or however you want, but you need to know its width and height. Let's say its width and height, right? We need to know how big this is and how big this is. Once we have that, then we can obviously find the area of the rectangle. Now let's take a look at letter B. How would knowing the coordinates of point A help us find the area? Well, pause the video now and think about that. Well, the y-coordinate of A, right, which is the distance from the x-axis up to A, that's going to be the height, right? So let me just write that down. Y-coordinate of A will be equal to the height. Now, the x-coordinate, I'd love to be able to say is the width, but whatever the x-coordinate is, if this picture is drawn somewhat accurately, is going to be negative. So really, it's the absolute value of x will be equal to the width. But once we find that x value, then we'll easily be able to just say, well, once we turn it positive, that's the actual width. All right, so now let's do it. Letter C. Find the area of the rectangle algebraically using the method of common bases. Show your work carefully. And as always, of course, whenever we want to find the intersection of two curves, we want to set them equal to each other and solve the resulting equation. So let's do that together and then have you work on finding out the actual area of the rectangle on your own. So to begin, what we want to do is we want to set these two equations equal to each other. 4 to the x plus 5 halves equals 1/2 to the 2x plus 1. And we want to use the method of common bases. Pause the video now and see if you can solve for the value of x, and if you can, then use the value of x to find the value of y, and once you have those two, see if you can then figure out the area of the rectangle. All right, well, I'm going to use a common base of 2 because I can rewrite 4 as 2 squared, right, to the x plus 5 halves. And I can write 1/2 as 2 to the minus 1 to the 2x plus 1. I can then distribute through. This is now going to be 2 to the 2x plus 5 because that 2 and that 2 in the denominator cancel. This one's a little bit easier. That will be 2 to the negative 2x minus 1. Now that they have a common base, I can now set the exponents equal. 2x plus 5 is equal to negative 2x minus 1. Add 2x to both sides, I'll get 4x plus 5 is equal to negative 1. Subtract a 5 from both sides, I'll get 4x is equal to negative 6. Whoops, I don't want to divide by x, let's divide by 4 on both sides. And I'll get x equals negative 6/4, but that is the same as negative 1.5. Negative 3 halves, negative 1.5. So that's my x-coordinate. Actually, maybe I'll mark it on the graph right now. Now, of course, what that tells me, and we discussed this already, is that the width of the rectangle is 1.5, but I still need to know the height. And in order to get the height, I can take my x value, of negative 1.5, and I can substitute it either into this equation or this equation to figure out what the y value is. All right, so I don't know, maybe I'll take it and I'll substitute it into y equals 1/2 times 2x plus 1. Actually, that's going to be kind of obnoxious because it's got that fraction in it. Then again, they all have the fractions. But let's substitute it into 4 to the x plus 5/2. All right, if I substitute my x in there, I'll have 4 to the negative 1.5, and I'll just maybe change that to 2.5 so it makes it easier. That's going to be y is equal to 4 to the first, actually. So that's 4. So the height of my rectangle is equal to 4. And now I can figure out the area, right? Last but not least, the area of the rectangle is 1.5 times 4, and that's going to end up being 6. All right, so a little bit tricky, you know, a little bit lengthy because you're doing a lot of different steps in order to get the coordinates of A. Well, that will then allow you to figure out that area. Let's take a look at one last problem. Exercise number 6. At what x-coordinate will the graph of y equals 25 to the x minus a intersect the graph of y equals 1 over 125 to the 3x plus 1? All right. And notice, of course, that all of our choices involve x equaling some expression that has an a in it. All right. So what I'd like you to do is pause the video now and see if you can figure out the correct choice. All right, well, just like before, in order to find the x-coordinate of the intersection, what we're going to do is we're going to take 25 to the x minus a, and we're going to set it equal to 1 over 125 to the 3x plus 1. Now, both 25 and 125 are nice integer powers of 5. So 25 is 5 squared, and 125 is 1 over 125 is 5 to the negative third, because 125 is 5 to the third. We can now use that product property to distribute. So I'll get 5 to the 2x minus 2a, and it's very important that both of those get multiplied by 2. In this case, we'll have 5 to the negative 9x minus 3. Now that we've got a common base of 5, we can drop the bases. I'll get 2x minus 2a is equal to negative 9x minus 3. All right, we just have to keep our wits about us. If I add 9x to both sides, I'll have 11x minus 2a is equal to negative 3. If I now add 2a to both sides, I'll get 11x is equal to positive 2a minus 3. And now I just need to divide both sides by 11, giving me x equals 2a minus 3, all divided by 11. And I believe, hey, that is choice 2. All right, so a nice little symbolic one. By the way, the reason that they might give you a problem like this is that, of course, if they didn't give you one that involves something like a, right, if this was just simply x's and whatnot, and this could definitely have been said about this problem, the last one that we did, you could have put both of these into your calculator, used the intersection command to figure out the value of x. Now, of course, they could easily give you this problem and say that you have to do it all algebraically, but the graphing calculator would at least help you figure out then whether or not you've done it correctly. A problem like this, very difficult to do it all on your calculator because of that sort of mystery value of a that propagates through the entire problem. All right, let's summarize. In this particular lesson, we saw one of the few techniques, pure algebraic techniques, that allows you to solve exponential equations, equations where the variable is in the exponent, without using your calculator in some way. All right. Now, I keep saying that because we will see some techniques, especially in the next unit, believe it or not, that will allow us to solve exponential equations probably quite a bit easier than the method of common bases, but we've got to bring technology in order to do that, which is fine. Technology is great. I'm not saying it's a bad thing. All right. The method of common bases, though, when it works by writing both sides of the equality in terms of a common base. If you can do that, if you can get, 2 to the whatever is equal to 2 to the different whatever, then you can set the two exponents equal to each other and solve. All right, and that's what we went through in the entire time. You will always want to be looking for common bases that are small, positive integers like 2, 3, 5, 7, numbers like that. You're probably never going to have common bases that are like 17. That's likely not going to happen. All right, well, I want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.